Alright, here we go. Let's get some part 2 of the notes here. So this is going to be some example problems, and just look at this guy. He's really happy. He's excited. Just look at that smile right there. Anyway, we're going to do, it's a quick recap of the previous video. List of facts, vocab, equations, and then a couple of examples. Here we go. Here is the vocab. So our big thing was momentum, and it's defined as mass times velocity. So our equation was momentum equals mv. So we were talking about how things can, or really what we can do is we can describe motion of things as a system and as a whole. So things that are moving at the same time, so more than one thing is moving, and we can describe its motion. And you can summarize it into two basic things, and they're both collisions. So two kinds of collisions. One of them is inelastic and the other is elastic. All they really mean is inelastic means they stick together, and elastic means they bounce apart. Here's what this looks like. Elastic, we have an object on the left here, and it's approaching this object on the right, which is at rest. And instead of bouncing apart, let's say that they were covered in Velcro, and they stuck together on impact. So when they collide, or when the one on the left collides to the one on the right, they stick together and then they move as one thing. So that's an elastic collision. An inelastic is the opposite. Let's say the same two boxes are there. The one on the left is approaching the one on the right, and this is more of a, if you've played pool, think of like one of the billiard balls colliding into the other one, where the first one basically knocks the other one out of place and then sits still if you hit it like just right. So the one on the left is colliding with the one on the right, and then afterwards what happens is the one that was sitting still is now moving, and the one that was moving is now sitting still. So they kind of traded motions here. Okay. We saw this equation before, but I'm going to rewrite it in this way, like this. And I'm going to tell you now, this thing right here, F delta T, that is actually a thing that has a name, and it's called the impulse. And so the impulse, what that means is it's equal to m delta v, which is a change in momentum. So the impulse is equal to change in momentum. So we're going to do a couple of examples with those equations and those kinds of collisions, and you can see how this works. So our first example is an object on the left is approaching the one on the right, and they have different masses. The one on the left has a velocity of 5, and then the one on the right has a velocity of 0. So my question is, if they stick together on impact, how fast will they move together after the impact? So we've got to use the main idea here is the momentum total before equals the momentum total after. So all of the momentum of every single object that we're talking about added together before and added together after is going to be the same. So what this is showing us here is this, let me point out what I'm talking about, this m1v1 and m2v2. Those two things are the momentum of each box before the collision, and then on this side, m1v1 prime, m2v2 prime, so these little things up here mean prime. All that is it's distinguishing the velocity of each box after the collision rather than before. So we add those momentums up after the collision, and they should be the same. So if we look back at our situation, one of them is not moving before, and it's the second box. So the one on the right has no velocity, so that means it's got no momentum. So it will simplify. And the other thing is, if they are moving together as one piece after the collision, then v1 prime and v2 prime are the same thing. So whatever that ends up being, it's the same number. So I'm going to rewrite my equation one more time. So all the momentum at the very beginning here is going to equal the momentum of both boxes moving together at the end. So I put m1 plus m2 because we can treat that as one massive object, and it's going to total to both of the masses added together. So when we simplify it one last time, we get this equation here. And so I'm going to plug in my numbers to this, and that's going to tell us what our final velocity is of both objects. So if you look back or rewind the video to the picture, those are our numbers, and I'd plug them all into my equation to find the velocity. Then we find that it's going that fast. So it's going significantly slower than the very first box, and if you think about that, it makes sense, because we've got a little bit of mass moving at some velocity, and then all of a sudden it collides with another piece of mass, and then they move together, and in order for that to make sense, it wouldn't speed up, and it wouldn't necessarily go the same speed either, so it would have to be going a bit slower. Here's our next example. We've got two objects approaching each other, and then they bounce apart. So this is an inelastic collision. So what we want is, we want to add up the momentum of each box before the collision, and then add them up after the collision. So we're using the same exact equation again, start in the same place, but it won't necessarily simplify the same way. So let's give a couple of numbers to our situation. Let's say before, we know that the one on the left is moving at 3 meters per second, the one on the right is moving -4 meters per second, and then their masses are 5 and 3, and just suppose that we measured this. I don't know if this would actually work, but just to get practice with the equation, let's suppose we knew that, let me back up. Let's suppose that we knew the velocity of object 1 after the collision. Let's say we knew it was -2. So it started at 3 meters per second to the right, and after it collided, it went 2 meters per second to the left. Just for the sake of practicing the equation, let's say that was true. And then my question is, how fast is the object on the right moving? So all we got to do is plug in all of those numbers into that long equation at the top, and then solve it for v2 prime. And if you do that, I'll leave that exercise to you. If you do that, you'll get 4.3. And notice how we actually have signs on these velocities. Remember, velocity is a vector, so it has directions. So in this example here, positive means it's moving to the right, negative means it's moving to the left. So when they bounce apart, this one's moving 4.3 meters per second to the right, where the other one is moving 2 meters per second to the left. That makes sense because when they collide and bounce apart, they go in opposite directions. Alright, let's do an example with our impulse equation. This one is actually from your book, and it's on page 341, if you want to look at that. And if you wanted to read a little bit more about it. This is a car, and it's about to crash into a wall. So they do this to test out safety features in cars, like seatbelts and airbags, and whether or not they work and how well they work. So what they do is they crash things in the walls and then see what happens. And then they can do things like measure forces and like see how much of an impact that would be on a person. So before the collision, it's going a certain velocity to the right, and it's going kind of fast. And then afterwards, it bounces back at a very small velocity. So let's give it some numbers. It was going roughly 13.5 meters per second to the right before it hits the wall, and then after it hits the wall, it bounced back at 1.3. So if we know the time that it takes where it's on the wall, so the time it takes to change its momentum, and we know its mass, then we can calculate the force. So I want to know, if that was me in the car and I crashed in that wall, how much force am I going to feel? Or how much force is necessary to change that car's velocity that much? So we're going to use our equation that we just talked about a couple slides back, and this is our impulse is equal to the change in momentum. So we want to know the force, solve it for force, and then we just have to plug in all of our numbers. And if you go back or rewind, you'll see these are the numbers. And if you plug everything in, then you should get the force. Now notice the way that I plugged this in. For change in velocity, I used negative 1.3 first, and then I used 13.6. So remember, in case you forgot, it's always the final minus the initial. So our initial velocity was 13 to the right, our final was negative 1.3. So what you're doing is you're actually going to add two negatives together. And when we get our force, it's also going to be negative, and it's huge. Why is it so huge? Well, we have an incredibly massive thing, and then we did it in a very short amount of time. So that's going to give us a large number divided by a very small number. We're going to get a very big number. Alright, those were two quick examples, or actually I think there's 3 examples. But those are the basics here for collisions and using the impulse equation. If you needed a recap, go back and listen to one of the examples again, and then if you're feeling confident, go ahead and try some of the problems.